Alright, welcome to the pycse channel. Today I want to talk about Numpy array algebra. That is, if we have two arrays and we want to add or subtract or multiply them, what are the rules associated with that algebra? So the first thing I want to remind you is that Numpy arrays, when you do regular algebra, and by regular algebra I mean not matrix algebra, just regular addition subtraction, is done element-wise. So we will normally import NumPy as NP, and let's make two arrays. We'll work with small arrays here. So let's say we have an array with 1, 2, and let's make another one np.array 3, 4. So these are one-dimensional arrays. You can tell they're one-dimensional because if we look at the shape of A, it has this tuple that's a single number with a comma that makes it a tuple. So this is only one dimension and it has two elements. And similarly, B has the same shape. So these are two one-dimensional arrays that we can see the shape of here. And that means we can add them because they have the same shape. And that just does an element-wise 1 plus 3 to get 4 and 2 plus 4 to get 6. We can multiply them. All of those things happen in an element-wise fashion. Now let's make another one-dimensional array that's a little bit longer. Let's say 1, 2, 3. Now this one has also one dimension, but it has 3 elements. So if we look at the shape here, then you can see that it is again one-dimensional. There's only one dimension here, but there are 3 elements. And 3 does not match 2, so if we try to add A plus C, then we get an error. And the error is operands could not be broadcast together with shapes. So the shapes here are 2 and 3, and what happens is there's nothing to add to the 3 over here, and so it's undefined, and that is considered to be an error. Alright, this also works in higher dimensions. So let's make a new array here that's 2 dimensions, np.array. And here we'll make this a list of lists. So here if I have this 2-dimensional array, and let's do np.I of 2. And so B looks like this, and if I look at B.shape, then here we see 2 by 2, and A.shape is also that. So if we look at this shape, now there are 2 numbers. That means it's a 2-dimensional array. And the first dimension is the number of rows. We have 2 rows, and the second dimension is the number of columns. That means we have 2 columns. And because these two things are the same, then we can add them. And all that does is add 1 to the diagonal here because the identity matrix has 1 on the diagonal and 0s elsewhere. So again, we have here element-wise addition. So as long as our shapes are identical, we can do all kinds of element-wise operations. And there's lots of times where you want to do something where the shapes are not identical for convenience. So let's say, let's look at A here again. Let's suppose I want to add an array 1, 2 to each one of these rows. So that is, I would like to do A plus, and I'll write this in shorthand like this. This would add this single 1, 2 to each one of those rows, and we get 2, 4, and 4, 6. Right? So here, if we repeat this in the way that this looks, then we are able to do the element-wise addition. Now I had to type out this array by hand. We could also use np.tile and give it the row that we want, 1, 2, and then we're going to repeat this in a shape. So the repeated shape is that it's going to be repeated as 2 rows. So So we'll do 2 comma 1 here, and that's going to give me that array. And so now I can also just have a plus this. All right, so what I'm showing you here is that we are doing element-wise operations when we do these kinds of things. And Python provides a shorter syntax. So I can just write a plus 1 comma 2, and it does the right thing. The right thing as long as you understand what this means. So here we have, again, a one-dimensional, I wrote it as a list, but let's make it an array just so we don't mix up too many ideas here at once. This takes an array that you know is one-dimensional with 2 elements and adds it to each row of this of A. That's called array broadcasting. And essentially the way to think about it is when Python can do this, right, it takes this 2-dimensional row and it stretches it to make it work. And it can do that because there are 2 elements here and there are 2 elements in A, and it basically just is equivalent to tiling it down the rows and adding it to each row. If this was a column instead, right, to get a column we have to have an actual 2D array. So let's say that let's look at A again so we can kind of get it back in our minds. If I want to add 1 and 2 to the columns instead of the rows, what I have to do is make this into a column vector. So let's do it by hand first. np.array. Here we have to make it a 2-dimensional array, right? And maybe it makes sense to write it this way just so you can see that we have a list of lists where each element has each row has 1 element. And now when we do this, we get 2 and 5 and 3 and 6, which is equivalent to adding these. Now this is pretty tedious to write out ourselves, and so there's a couple of ways that we could get to it. So let's make x be this little array up here. All right, and then we'll look at x and x.shape just to remind ourselves what we're looking at. So we have x is the array, and it's a one-dimensional array. So we have a couple of options now to get x into a column vector. One of them is reshape. So we can call reshape on here, and this is a built-in function on arrays, and we can now give it the new shape that we want. So the new shape, instead of 2 comma, is that we want 2 comma 1. Right? So this is going to now reshape this one-dimensional array into a new array with 2 rows and 1 column. And that gives us this thing that we want. Now, what's critical when you do a reshape is that the number of elements obviously has to stay the same. I cannot make this into a 3 by 1 because there are not 3 elements, and we'll get an error that it cannot do that. Okay, and then the other thing that is sometimes you'll see is that sometimes people will put a -1 at the end, which is a way of saying make it have 2 rows and then make this dimension whatever it needs to be to fit. So that way we don't have to calculate what that is. And that's more useful for higher dimensional arrays. Okay, so now once we have this, now it's easy. We can just add A, and it will get broadcast into that shape that is necessary. And this is equivalent to something like np.tile. And so now this is a column vector. And if we wanted to repeat this, we would say, I think 1 comma 2, and that's going to have it be repeated as 1 2 1 2, so that we are repeating the column vector 2 times in the column dimension. Right, so kind of like that. Now, this is not the most convenient kind of syntax that people like to use, and so there's an even cleaner syntax that people use. So let's go back down here and review what our big A vector is, or big array. So here we have our 2-dimensional array, And I already showed you that we can do just do this. So here we're going to add 1 and 2 to each row, right? And this is the simplest form of array broadcasting. Now, to get this to work in terms of columns, we could do a reshape. So I could do this. Like that, and now it's going to do it column-wise. But what's more common is this idea of expanding this array. So before we get to putting it all together, let's go back to X. X is this one-dimensional array. We can expand it like this. So if we use indexing and say take all of the elements but expand one dimension here, then this converts it from a one-dimensional array to a two-dimensional array, and it expands by adding a 1 here. Sometimes many people prefer to do np.newAxis, and this is a symbol, if you want, in the Numpy library that indicates that what you're doing here is inserting a new axis. It turns out, though, that np.newAxis is just equal to none. And so instead of writing this long thing, I almost always just write none. All right, and so now to get the column-wise addition in here, we just have to say a plus x with this expansion like this. All right, and that gives us the column-wise addition. So this is now the simple syntax, the short syntax or syntactic sugar for taking this array, turning it into a column vector, tiling it along all the columns, and then adding element-wise to A. And that's the general nature of broadcasting. So the rules why this works is if we look at the shapes, we have a 2 by 2 here and a 2 by 1 here. So the element-wise addition or broadcasting rules are anytime the shapes are the same, you can do it, no problem. And when the shapes are not the same, if the last element of one of these is a 1, then it can be expanded in that dimension to fit all of the other ones. And to illustrate that you can't just do any old version of this, if we were to put none in the first place and then expand like this, then it gives us, this is the row addition. So this gives us now a 1 and a 2, so it's one row with 2 columns. And so this is able to be broadcast to each of the rows in here. All right, let's see a couple of other interesting things that could happen with broadcasting. So we said earlier, if we have, let's do n is np.array 1, 2, 3. And let's do O is np.array 0, 1. All right, we know that n plus O is going to be an error because also because I have syntax error. But even when we fix that, we have these shapes could not be broadcast together. But if we expand these in the right way, then we will be able to do this addition. So what we have here, let's look at the shapes. The shapes are 3 and 2, like this. So let's try expanding these. like this. Let's see what we get. Okay, here we have expanded n. So we've taken this and basically turned it into a column vector. And now we're adding it to each of these rows in O. And so what we get is 1, 2, and 3 plus these. So we get 1 and 2, 2 and 3, 3 and 4. So if we look at these shapes, then we have 3, 1, and 2. So basically this is getting expanded into 2 copies of 1, 2, 3. Right, so let's look at it piece by piece. So we have this one, and then this is like tiling this one. 1, 2. So that gives us copies of the array like this. And now the O array is 0, 1, so that's also not quite element-wise. So let's look at that one. np.tile O, and now we want to do this one, 3, 1. That gives us 0, 1, 0, 1, 0, 1. And now we can take these two things and add them together. And we get 1, 2, 3, 1, 2, 2, 3, 3, 4. Okay, so this short syntax here is equivalent to this really long syntax here, where you have done all of the tiling to get each array into a compatible shape to do element-wise operations. Now, this is really short and easy to write, but it really hides a lot of work that's being done in terms of tiling and repetitions and getting everything element-wise. And it's a little less obvious, actually, what's happening here compared to what's happening down here. Now, this might not be obvious to you either. In fact, maybe we should rewrite this one as n.reshape 3, 1. Now it's totally syntax free and just using regular functions to do these operations. So this kind of broadcasting is done very, very often in machine learning, in linear algebra, in managing Numpy array algebra, and it's kind of a balance of, do you write this really long explicit code that tells you how you're reshaping and how you're tiling to get things into the same shape, or do you use this kind of very short, terse syntax for generating the array algebra? So hopefully what you've seen today is that there are ways to do all of the array algebra by explicitly constructing element-wise operations on arrays that have exactly the same shape, including when you have to construct that array by reshaping and tiling to make it work on every row or every column. So you can always do that in your code, but you can also see that down here at the end, that code can end up being kind of complex looking and long while you work it out. And Numpy broadcasting uses this really short syntax where this is equivalent to reshaping an array by adding an extra dimension, and then the broadcasting rules allow this to be all done automatically without you having to do these things yourself. And eventually that has some advantages when the arrays get really big. Here, if O was a very large array, say it had thousands of elements, then you might not want to be using an approach like this, because this is going to make a temporary array that has to be created, that takes time and memory. And this also does that as well. And this syntax up here will do all of that in as efficient a way as it knows how to. Now, when you get to really big arrays that take up a lot of memory, sometimes you have to be even more clever in how to avoid making temporary copies. But that's a very advanced topic that we won't have time to do today. All right, so that's basically it for today on talking about how to do array algebra and why this kind of fancy syntax and idea of broadcasting exists to avoid this longer syntax down here. All right, thanks for listening, and I'll see you next time.